Welcome everybody to another video. Last time we introduced the notion of conformal transformations. Conformal transformations are maps that preserve angles. And we had this chart here in which we were trying to put some order into the notions we've learned and to specify which properties they actually have. So the two properties we were interested in were preserving lengths. Such maps are called isometries or rigid motions, or preserving angles, and such maps are called conformal maps. So we know that rigid motions preserve lengths. That's by definition, right? This is by definition. And last time we also proved that rigid motions preserve angles. On the other hand, we know that inversions do not preserve lengths. So the question is, do they preserve angles? And this is perhaps one of the more surprising things about inversions. I mean, inversions are not very nice transformations like rigid motions, in the sense that they really distort shapes. Rigid motions, whenever you start with a triangle, you end up with a triangle. If you take a line, you end up with a line. You start with a circle, you end up with a circle. However, as you have seen, this does not apply to inversions. Inversions are sort of not the nice; they're sort of the naughty transformations, in the sense that they can take a little circle, right? So if this is if this here is the circle of inversion, they can take a little circle that goes through the center of inversion and essentially blow it up to an infinite line, to a line of infinite length. They can also take a circle that does not go through the origin and then make a bigger circle out of it. So definitely inversions do not behave nicely with respect to shapes. They stretch things, they contract things. They can even stretch a finite circle into an infinite length object like the line. So it might come as a surprise that inversions should preserve angles. That is definitely somewhat. That might sound somewhat bizarre, because if they behave so badly, why would they? So they sort of behave so badly with respect to lengths. They don't respect them at all. They do seem to have some sort of niceness built into them, in the sense that they preserve angles. So this is going to be a theorem, right? So I'm going to put a yes here tentatively. And we're going to see in the next video the proof of the theorem that inversions actually do preserve angles. However, in this video I wanted to just give you a few examples of how this happens, so that you can visualize how inversions do that. So let's state it as a theorem here. A theorem that inversions are conformal maps, and the proof will be included in the next video. So let's actually see on the pictures how this works. Alright, and we begin with a very simple example, namely here is the center of inversion. and the orange circle is the circle of inversion. And we're going to start with a very simple situation where we take two lines, and one of the lines is going to go through the center of inversion, and the other line is going to be perpendicular to it. So we have a right angle between these lines. So let's call them M and K. So what happens to these lines when you apply inversion to them? First of all, the line M, because it goes through the origin, through the center of inversion, it's mapped to itself. So the line M is equal to M prime, and that's just ICK of M. Right, so K here is, of course, the radius. So this is of radius K. However, what happens to the other line? So we learned in the past few lectures how you can construct the images of lines under inversions. So first of all, this line K does not go through the origin, so I know the image of that line will be a circle. So how do I construct the circle that is the image of that line? Well, I draw a perpendicular line from the center of inversion to that line, but that's actually the line M, so I already have it. And this is the point where they intersect, and I would like to know where this point is mapped under the inversion. Once I know where this point is mapped, I will have a diameter of the circle to which this line K maps. How do I get that? Well, I just go from this point and try to draw a tangent line. Okay, that actually worked. I didn't expect it to work. It's almost tangent. Okay, so now I project it down here. And if this was point H, then this is point H prime. So the line segment CH prime is the diameter of the circle that is the image of K. Okay, so that circle here, that's IC, okay, of K. Oh, by the way, not a great notation, right? To call the radius of the inversion K and also this line K. So let's change the name. Let's call this line N and this N here. Okay, all right. So the angle between the line N and the line M was 90 degrees. What's the angle between the images? The image of line M is the same line, M prime, and the image of the line N is that little circle here. What does it mean to measure the angle between a line and a circle? You measure the angle between the line and the line tangent to the circle. Oh, but look, this dotted line is actually exactly the tangent line to that circle. And lo and behold, that angle here is 90 degrees. So yes, the angle is preserved, but that was kind of a giveaway, right? I mean, one of the lines was going through the center of inversion, so it was transformed to itself. So maybe this wasn't really a general enough example. So let's complicate things a little bit. Okay, I'm just trying to preserve this beautiful artistic circle, only now I see the flaws of it. Oh my god. Alright. Still looks like not a perfect circle. Almost. Okay, so that's the circle of inversion here, C. And now I'm going to take two lines like before, line M and line N, and I'm going to intersect them now at the right angle, but so this is going to be my line M. Actually, I think it was called N last time, so let's keep the red line as N. Should have used R, this way I would know, but I haven't. And then another line, let's say, going also at the right angle, because kind of right angles are easy for me to recognize. So here is the right angle between. So now I will try to construct the images of these two lines, and because none of these lines now goes through the center of inversion, I know that the images of both of these lines will be circles. So let's construct them like before. So first, I draw a line perpendicular to the blue line that goes through the center of inversion. Okay. And then I use the tangent line. So of course the point is, here's a point H, and I would like to know where this point goes. So again, I draw a tangent line from here. I'm really getting good at drawing tangent lines. Okay, it intersected somewhere here. Go perpendicularly, and that's H prime. Okay, so now the CH prime is the diameter of the circle that is the image of the blue line. So in blue, here's a circle. So that is ICK of M. That circle. Now what happens to the red one? So I do the same thing. I draw a line perpendicular to the red line. So that's going to be, all right, I already used up the letter H, so how about I just call this something else, maybe G, okay? And so now I want to construct G prime. So how do I do this? Again, I draw a tangent line. Of course, it doesn't matter which side I draw the tangent line, here or here, but I kind of try to do it where I have less things drawn on the board. So it intersects, wow, mine intersects at many points, but it should only intersect at one. So this is going to be G prime. Okay, so I have now the diameter of the second circle, which is the image of the red line. Now let's see if I can get it done. So here's the circle. Oh. Almost. Okay. Two questions, right? The circles intersect in 2 points, while the lines intersect only at 1 point. How is that possible? And which point of intersection corresponds to the point of intersection of the lines? Well, look, these two circles intersect at C, and that point C doesn't have an image under the inversion. That's in projective geometry, the image of this point would be the infinity, so you don't see this on this picture. So this point is mapped nowhere under the inversion. So that point sort of doesn't count. That's the point that corresponds to that one. So I'm going to now mark that point of intersection here as A, and this now is A prime, where A prime is the image of A. Okay, so the question is, what's the angle between these two circles at A prime? So I need to draw tangent lines. I'm really running out of colors here. But here's the tangent line to the blue circle. Okay, and the pink color will be the tangent line to the red circle. And what's the angle between them? Yes, 90 degrees. The angle is 90 degrees. So again, it looks like it all works. And look, I'm going to sort of change the way I marked the previous angle. So here I'm going to put the right angle. Okay? But to be completely precise, that angle does not correspond to this one, but the one that's on the other side. Of course, for right angles, it doesn't matter, right? If two lines intersect and one of the angles is right, then all the other three are right. But once we get to angles that aren't right, it will actually matter. So why do I mark this angle corresponding to that one? Because remember what inversion does, right? It takes the points that are closer to the center of inversion and maps them to points that are further away from the center of inversion. So if I draw these sort of two arrows on these lines, if I were to orient these lines, then this part of the line is now closer to the center of inversion than A. Therefore, that part of the line would actually be mapped to the part that is further away. And similarly here, that arrow that gets sort of closer and closer to C as you go here, it will be mapped to this point, which gets further and further away. You see, right, if you actually keep going along this line, the points are getting closer and closer to C, while these points here are getting further and further away. Once they get to H, they start going further and further away, and then you just sort of make a full circle on that circle, and your points on the circle are getting closer and closer to C. That's why it's these two angles that correspond to each other, so are these two here. But in any case, the lines intersected at the right angle, and you see that the circles also do. Alright, so let's throw a final challenge at this. I mean, I'm sort of playing with you here, right? These challenges are sort of pointless. There's a theorem that says that inversions are conformal maps, so it's always going to work. But it's kind of nice to see how you try to construct something that looks like it's not going to work, and in the end it works. It's sort of very interesting that these inversions that behave in such a weird way do have some very strict laws that they follow, and in particular one of those laws is that they always preserve angles. Okay, C and the circle of inversion. Of radius k. Here's what I'm going to do. I'm going to inscribe an equilateral triangle into that circle. So inscribe an equilateral triangle into the circle. Okay, and now I want to know, so I know all the angles. All the angles are 60 degrees, right? So let's try to find the image of this triangle under the inversion. So I'm going to try to find the image of every single side of this triangle under the inversion. So let's first work with the blue side. And you see, I already know the blue side is of course part of a line, and this line does not go to the center of inversion. So the image of this line would be a circle. I know that the circle would have to intersect the orange circle at these 2 points, because that's the points where the line intersects the circle of inversion. However, of course, I just want to draw part of that circle, not all of it. So if you know that the circle is going to go like this, and it's going to go through the center of inversion, you might ask, okay, so does this line segment map to that part of the circle, or to whatever is outside? Okay, what do you think? Inversions always map things that are inside the circle to things that are outside of the circle. So that means this line segment will actually be mapped to something that lies outside. At the risk of making this picture really difficult to read, I am going to try to find the diameter of the circle. So again, I construct a perpendicular ray going from the center of inversion to the perpendicular to the line segment, and I have to extend it further out. Okay, and then I need to look at the line that is tangent here. Okay, my straight lines definitely don't look straight. So if this was H, this is going to be H prime. So now you see what your circle is going to be. It's this circle whose diameter is CH prime. Okay, I'm only interested in the outside part of the circle, not in the inside. So I'm going to connect these somehow. Now this looks terrible. Doesn't look like a circle, like part of a circle at all. So maybe I'll try to go from here all the way out here. Okay, that's the outside part, right? And the circle sort of closes in here. Yes, maybe the point H should have been actually placed a little further away. But in any case, you get the idea here that blue part is where where this line segment, the blue line segment, gets mapped. So let's see what happens to the black line segment. It's the same thing, right? I would construct again something similar, and then I would get a circle that goes through C out here. Again, doesn't look so good. And then it connects through C. Still doesn't look very good. Okay, maybe a little better. Alright, and the red one also maps to a circle that looks like this, or part of a circle that looks like this. You connect these two. Alright. So what about the angles then? So, by the way, that triangle right inside got mapped to this thing that looks so bizarre. Of course, it's actually equal size on every side. So I'll just make this a little bit. It really hurts my eyes this way. I must have drawn the tangent lines incorrectly here, so it's... Okay. So the point H, probably if I drew the tangent correctly, it would have gone all the way here, and this is the H prime. Okay, so this, that, and that is the image of our equilateral triangle. And now let's look at the angles. Okay, where would this angle go? Well, first of all, this point goes to itself. And the things that are inside the circle go to the things that are outside the circle. So you should draw tangent lines now to this blue circle and to the black circle. But you see that these tangent lines are actually just extensions of this line and that line. And the angle here indeed is 60 degrees. And so it is here. And so it is here. So all the angles are actually preserved. Okay, so you can draw more examples like this at home. It's kind of a fun thing to do, actually, to try to construct the images of various figures that and lines and circles that intersect at different angles. But it's time for a proof. So next time, in the next video, we'll actually prove the theorem.